We're very honored to have our Minister without portfolio and Minister of National Science and Technology Council, Minister Wu Chengwen, to join us. Let us give him a warm applause. Let us welcome Minister Wu. 欢迎吴成文政委兼国科会主委。热烈掌声欢迎主委，还有呢所有呢来自世界各地海外的贵宾，非常荣幸有您的参与。It's time for the opening ceremony of FUTEX 2024。2024未来科技馆开幕典礼正式开始。Welcome to FUTEX 2024. Minister Wu, Secretary General of Canem Sinica 陈君厚秘书长，以及 Counselor of Ministry of Health and Welfare 刘明勋技监 ，Senior Specialist of Minister of Education 陈玉君专委。Ladies and gentlemen, our honorable guests from overseas, good afternoon. Welcome to the FUTEX Pavilion, FUTEX 2024. FUTEX is co-organized by the National Science and Technology Council, Academia Sinica, Ministry of Education, and Ministry of Health and Welfare. This year, FUTEX is themed Global Research Collaboration with Taiwan, bringing together cutting-edge research achievements from various fields, both domestically and internationally, creating a grand event that fosters potential innovation in science and technology. 今年我们非常荣幸，还有很多的贵宾跟我们一同来到未来科技馆2024的现场。国科会的吴主委、中研院的陈君厚秘书长、卫福部的刘明勋技监、教育部的陈玉君专委以及现场的朋友们，大家午安，大家好，我是刘姿玲。今天呢，非常荣幸跟各位呢一同来参与的是由国科会携手中研院、教育部、卫福部打造的未来科技馆。今年的主题呢，是以全球科研链结台湾为主轴，汇集了海内外所有科技研发的成果，打造潜力创新的科技盛宴。Today, we have distinguished guests from overseas to join this grand event. Now, please allow me to introduce, and later, if your name is called, please stand up, wave, and say hi to our audience. Let us welcome the Nobel Prize in Physics 2022, Professor Alain Aspect from Université Paris-Saclay. Oh. Bienvenue. Professor Cai Zhaoshen from Tokyo University of Science. Yokoso. And Mr. Yoha Variainen, Global Affairs Officer and co-founder of IQM. And Dr. Nicolos Maski, CEO and co-founder of Quandela. Benvenuto. And Signori Roberto Mauro, CEO APAC of Pascal. Benvenuto. 今天呢，非常有很多的贵宾远道而来。那当然来到这一次的盛宴呢，其实就是要进行今天呢量子科技论坛。那包含的讲者之外，我们有很多其他海外的贵宾共同的莅临现场。Besides our speakers, we also have our foreign friends, our overseas friends from France, New Zealand, United States, United Kingdom, Israel, Australia, and Singapore to join us today. So please stand up and wave to everyone. Let us give them a big round of applause. 请所有的贵宾起身 or you can just wave and say hi. Thank you. Thank you for coming. Thank you. Thank you. Thank you. Don't be shy. Thank you. 好，接下来呢，其实今天呢，很多的贵宾呢，就是隐身在我们的座位区当中，稍后呢，有更多的时间可以进行交流。那么在今天的一开始，我们要有请我们的大家长。Now we would like to invite our leader, Minister 吴成文主委 to have the opening remarks first. 让我们欢迎我们的大家长、行政院政委兼国科会主委吴成文主委上台致辞。
Good afternoon, all the distinguished guests, ladies and gentlemen. It is really my honor and privilege to welcome you to this Future Tech Pavilion, which is hosted by the National Science and Technology Council. And it has also been my greatest honor that I can meet Professor Alan Aspect consecutive 2 days. Yesterday, we were in the Quantum Taiwan 2024, the international conference, and also Professor Tsai and all the distinguished speakers. We met yesterday, and I was sitting in the room listening to the speech, keynote speech made by Professor Alan Aspect, which was very inspiring to me. I never got to know quantum technology before, but after yesterday's talk, I know a little bit, which is really very inspiring. And I was going to sit in this room again, but unfortunately, I have to leave after this opening. And I asked my colleague to record your speech later on in the Quantum Technology Forum. And I understand that it is a very rare occasion that Alan can come to Taiwan. It's a very precious moment because he is not just one of the very important person who can really explain quantum entanglement to ordinary people. It's very difficult, very difficult. I have been asking so many physics professors, what is quantum entanglement before? I never get to understand a bit. But this is really important because we are going to develop technologies for the real applications in the future. And it's very important for ordinary people to understand that so that they can give you the requirement, what you can solve, what kind of problems, what kind of applications, which is best for this quantum technology. Is it some kind of computing just like the computer today, or is it the communications that we want to make it safer in the future, or any other applications? So for this kind of gathering for the experts to discuss the quantum theory and technologies, of course it is very important. However, we are going to show ordinary people in this exposition that, well, quantum technology is not so far away from us, but it is closer, getting closer and closer to all these applications in the future. If we can bridge this gap, then together we can make the world better in the future. So I'm looking forward to the discussion later on in the workshop, the quantum technology workshop, so that we can let these people, they are already developing technologies in different applications, and maybe in the future they know that quantum technology can help. So if we can do that, it would be very wonderful. So I'm looking forward to that. And once again, I thank all the attendees. I know most of the people are here for you, just for listening to you, not for me. So I'll make it short. Thank you again. Thank you.
好，谢谢主委给大家的祝福与感谢。那我们接下来要请主委在台上留步 ，Please stay on stage for the group photo together. Today we are very honored to have our distinguished guests overseas, so from various backgrounds to see the outcome of pioneer technology together at the Future Technology Pavilion. So next, we would like to invite our guests to the stage for a group photo by following order. 今天呢，有来自现场以各界的贵宾，所以呢，接下来在这个难得的产官学研盛宴场合，我们要一起见证前瞻的科研成果跟交流。所以接下来要请主委跟我们的贵宾一同来进行大合影。首先邀请到的是国科会的苏正康副主委 ，Vice Minister of National Science and Technology Council。 中研院的陈君厚秘书长 Secretary General of Academia Sinica 陈君厚秘书长，卫福部刘明勋技监 Consular Minister of Health and Welfare 刘明勋技监，以及我们的教育部陈玉君专委 Senior Specialist of Minister of Education 陈玉君专委。紧接着我们要邀请到的是论坛的贵宾。Next, we would like to invite our distinguished guests of the forum, Professor Alan Aspe of Université Bakisakle, Professor 蔡兆生 of Tokyo University of Science, 量子系统推动小组执行长张文豪 CEO of Executive Officer Taiwan Quantum Program Office, Dr. 张文豪。Senior Vice President of Compo Electronics, Mr. 陈锡冠，人保电脑的陈锡冠资深副总。Global Affairs Officer and Co-founder of IQM, Mr. Yoha Variani. CEO and Co-founder of Quandela, Dr. Nicolo Samaschi.CEO APEC of Bascal, Mr. Roberto Maolo. Okay, please look at the cameras in the middle. Thank you, with a big smile. Thank you. 请看一下中间的摄影师。Okay, in the middle, please. Yeah, look at the camera in the front. Okay, thumbs up. Okay, please. Thank you. Very Taiwanese culture.Please give them a big round of applause. Thank you. 再次热情掌声，感谢大家的参与。Okay, please stay on stage. We will have other guests to come for the next session. 我们第二阶段的合影贵宾，我们共同的邀请我们科技办公室的杨嘉玲执行秘书、产学处的许增如处长，以及自然处的赖明志处长、工程处洪乐文处长。生科处杨台红处长，科国处李旺龙处长，前瞻处蔡妙慈处长，资讯处周子元处长，人文处郑琼芬副处长，竹科管理局陈宗全局长，中科管理局许茂兴局长，南科管理局的林秀珍副局长，国研院林博文副院长，国家太空中心吴宗信主任，国家灾害防救中心陈宏宇主任，以及国家同步辐射研究中心徐家宏主任。We would like to take a group photo all together. Okay, please step a little forward. Yeah, okay. Okay, please listen to the cameraman. Yeah, he's adjusting the position of where you stand. Okay? 还有要调整的地方吗？来哪边？好，来哪一位？好，都调好了吗？ Okay, still adjusting the position. Just a little bit, yeah. 好，哪一位要喊一下哦？来麻烦一下。好。The people step forward in the back. Okay, please look at the camera in the front. Thank you. One more, please look at the camera in the back. Okay, in the back. Camera in the back. Okay. Okay, big smile, please. Thank you. Okay, once again. Okay, the second row. Please have the thumbs up. Yeah, okay, thumbs up for the second row. Yeah, okay, thank you. Please look at the cameraman. Thank you. In the front with a big smile. Thank you. Thank you very much. Please take your seat. 再一次的掌声给我们所有的嘉宾。Give them a big round of applause. Please take your seats. Thank you. 接下来的时间呢，其实刚刚呢，主委也有提到，就是要进行今天众所期待的开幕论坛了。我们呼应呢，未来科技馆的展出，其实在这一次的展馆当中，不仅呢是展示前瞻的研究成果，我们更希望可以透过这个平台来搭建包含了产学合作的基础，让技术呢可以走出实验室。所以今天的论坛内容，我们会从 科研到产业量子科技的实践之路为主题。我们特别请到的是2022年诺贝尔物理学学奖的得主。他呢要来进行的就是今天从科研到产业量子科技的实践之路。Next, we will begin today's opening forum. In line with the Future Tech Pavilion exhibition, our goal is not only to showcase cutting-edge research results, but also to build a foundation for industry-academia collaboration throughout this platform, bringing technology out of the laboratory and into the real world. So therefore, today's forum is themed From Research to Industry, the path to quantum technology implementation. And we are very honored to have Professor Alan Asper from Université Paris-Saclay, the 2022 Nobel Prize laureate in physics, to deliver a keynote speech titled From Research to Industry, the path to quantum technology implementation. So now, let us give him a warm round of applause to welcome him. Welcome, Professor Alan Asper. Bienvenue.
I will try the Taiwanian way. Good afternoon. Thank you. Yes, what I like to explain, especially in an exhibition like that one, is that the path from basic research to applications is definitely very long. I like to explain the development of quantum mechanics. And by the way, you can buy a small book in Chinese. The English title is Einstein and the Quantum Revolutions. It's about Einstein, but it's about quantum mechanics. It's not about Einstein and relativity, because Einstein was a major player in quantum mechanics, and he was a major player in the first quantum revolution and in the second quantum revolution. So let us tell me a little bit that story to illustrate how long is the path to go from basic research to applications. Quantum mechanics emerged in the beginning of the 20th century because physicists had observation they could not understand. For instance, the light emitted by matter when excited, they could not describe the quantitative properties of that light by using the physics that they knew. Physics was quite developed at the end of the 19th century. Classical mechanics, Newton, motion of planets, etc., has been well established. Electromagnetism had been well established. Maxwell in 1865 has written a series of equations that we still use for describing electromagnetic fields, etc. The interaction between charged particles and matter was understood. So normally, people had all the tools to describe matter, the way in which matter emits light, the way in which it absorbs light. But when they were trying to make sense of what they observed, it did not work. It did not work at all. I will not go into the details of the properties of radiation, but I want just to mention one point that everybody should understand. They knew that matter was made of charges, positive charges and negative charges, with as much positive as negative charges, so that matter at the end is neutral. And they knew that charges with opposite sign attract each other. Positive charge attract negative charge and vice versa. And so if you think that you have positive and negative charge in a piece of matter like that, positive and negative charge should attract each other and matter should collapse. Why is it? that it did not collapse. It took the hypothesis of extraordinary behavior, impossible to understand in a classical way of thinking, to understand why matter does not collapse. And that new concept is called wave-particle duality. Wave-particle duality was first understood by Einstein about light. Einstein understood that light, which is a wave according to what had been established clearly at the beginning of the 19th century by Thomas Young in England, Augustin Fresnel in France. They have established the fact that light is a wave. They did not know the nature of the wave, but after Maxwell's equation, it was clear that the wave was electromagnetic. So by the end of the 19th century, there was no doubt light is a wave, and all optical phenomena can be described assuming that light is a wave. But Einstein spotted a few phenomena where he said these phenomena, you cannot understand them by assuming that light is a wave. You must assume that light is made of grains of energy, like small particles, but particles going at the velocity of light, because we are talking of light. And this particle, Einstein called it Lichtquanten in German, which means quantum of light. Nowadays, we call them photons, okay? And so Einstein understood that some phenomena will be understandable only if you introduce this idea that when you have a beam of light, in fact, it's a beam of small particles called photons. But on the other hand, he knew his physics. He was a good student. He had studied classical optics. And he knew that there are many phenomena in which you must describe light as a wave. What can you do? Well, Einstein was not a man to hesitate. He would be ready to change all our concepts. In 1909, we have to accept that the wave-like behavior and the particle-like behavior of light both exist, although they look to us contradictory. Yes, they are contradictory, but anyway, you have to accept two. Okay. 14 years later, my compatriot, Louis de Broglie, in 1923, made the reserve reasoning. Einstein, I told us, we think that light is a wave, but it is also a particle. What Louis de Broglie did is say, we think that electrons are particles. Yes, they are particles. When an electron bumps into an atom, the atom recoils, etc. There were observations of that kind. But we must also consider them as a wave. And he wrote a formula associating a wavelength, which is a characteristic of the wave, as a function of the velocity of the electron. And almost immediately, it allowed physicists to understand some observations. First, the idea that the energy levels of atoms are quantized. Bohr had made an hypothesis. Nobody really understood where this hypothesis came from, but it turned out that by making his hypothesis, Bohr could describe the property of light emitted by atoms, and in particular, the atom of hydrogen, which was one of the problems that physicists did not understand before the invention of quantum mechanics. So Bohr had made an hypothesis that people did not really understand. And then, when de Broglie comes with his assumption that an electron is a wave, immediately the quantization condition of Bohr became clear. The idea is the following. The model of the atom, invented by Rutherford, which is a good model, it has to be refined, but it is a good model, good starting point, is the fact that you have a nucleus which is positive, and you have electrons turning around. And it's just like satellites around the Earth, or just like planets around the sun. But according to Bohr quantization rule, only some orbits are permitted, and it is by jumping from one orbit to another orbit that the atom absorbs or emits light. But why this orbit? Well, with de Broglie hypothesis of wave-particle duality, you can immediately understand. If you think that the electron propagating on its orbit is a wave, after one full turn, the wave must return in phase with the wave that you had before. In other words, the number of wavelengths that you have in the length of the trajectory must be an integer number. Otherwise, you are oscillating like that, and after a turn you are oscillating differently, doesn't work. It's not stable. So this condition of stability of the wave after one turn was just what you needed to understand Bohr condition of quantization. This was 1923. When you have a wave, all physicists look for the wave equation, an equation of which the wave is a solution. And a physicist, mature physicist, a mentor, told the young Schrödinger, you are gifted. If there is really a wave, like this Frenchman says, there should be a wave equation. Look for the wave equation. Find the wave equation. And this is what Schrödinger did. Schrödinger found the wave equation of which the de Broglie waves were solutions. And then it was the Schrödinger equation. And once you have the Schrödinger equation, you have all modern quantum physics. It has been slightly refined by Dirac, who published in 1930 a beautiful mathematical formalism, of which Schrödinger equation is only one version of that formalism. But so I mean that in 1925, everything was set. We had the equation to understand why matter is stable, why the electron remains at a distance from the nucleus and matter does not collide. We had the equation to understand the chemical bond between atoms. For instance, in the hydrogen molecule, you have two hydrogen atoms. Why are they fixed to each other? Why in a piece of carbon do the carbon atoms are maintained close to each other? Schrödinger equation allows you to understand that. And after the work of Dirac, you can also describe how light is emitted or absorbed by matter. This was 1925. And so I am speaking of the first quantum revolution, and what we have seen already in this first quantum revolution is a conceptual revolution, wave-particle duality. And now we have a scientific revolution. Now we have the tool to understand why matter is stable, how matter emits light or absorbs light, etc. So it's a scientific revolution. Now, there is a third point of view in a revolution. The third one is application. Do we have application? Yes, but it took a long time. First real application of quantum mechanics, transistor, invented in 1947, 22 years after the establishment of the Schrödinger equation, more than 40 years after the first ideas about quantum mechanics, 4 decades, and 22 years after Schrödinger equation. And you know how they discovered the transistor? Not by chance. The people who discovered the transistor were the best physicists of that time, trying to use Schrödinger equation to describe accurately the motion of the electron in matter. Okay? And they succeeded. And then they began to apply this idea to some strange materials called semiconductors. And they got an idea. If I would have a semiconductor positively doped and a semiconductor negative doped, maybe something interesting would happen. And so they asked the engineer, do we have such materials? And the engineer say no. And so the physicists say, work hard. And so engineers began to purify the materials. And after purifying, injecting right the exact amount of impurities they needed. And eventually, they could build the first transistor, which is at the root of all modern electronics. You are going to tell me, come on, integrated circuits are not transistors. Yes, they are transistors. A microprocessor is millions, billions of transistors on a chip. So once you have the transistor, you need another 2 decades to invent integrated circuits. And notice, all these things are not made by chance. It's people thinking hard, using the law of quantum mechanics, and the proof is that at the end, not only they have a beautiful invention, and probably they make a lot of money with this, but they get a Nobel Prize. So it's really to say that this development of technology took time and took the best mind to do it. The other example of the first quantum revolution is a laser. Without laser, you have not information highway. You have not fast communication through optical fibers. If you take a normal lamp, a classical lamp, you try to inject the photon in the optical fiber, basically there is nothing. No power can pass through the optical fiber. You need to have a laser. The laser was invented in 1960, 60. And the equations which are at the root of the working of a laser were invented, were discovered in 1916, 16. By whom? By whom? Einstein. This is why I write this book saying Einstein and the quantum revolutions. Einstein is at the root of so many things. The equation for absorption and emission of light by matter, the basic equation, have been written by Einstein in 1916, 16, and the laser was invented in 1960, 60. Think of it. So if there are venture capitalists here, know that your investment has to be very long-term, okay? Now, second quantum revolution. They told me 20-something. Okay. Second quantum revolution. Second quantum revolution is based on entanglement. Entanglement is a property yet more counterintuitive than wave-particle duality. Wave-particle duality is about a single particle. What is strange is that you have both properties, but at least each property, I can describe it easily in our space. If I speak of a particle traveling in our space, well, everybody understands what it is. I can throw a ball, it has a trajectory, etc. If I describe a wave propagating in our space, you need to have done only a little bit of physics or mathematics to understand what is a wave, which propagates and fills the space. What is strange is that you have the two properties for the same object. Sounds contradictory. It is contradictory, but it is a fact. But at least each concept, I can describe it in a rational way in our space. Entanglement, you cannot. I don't know any way of describing entanglement simply in our state, or I have to introduce a crazy concept, which is non-locality. Spooky action at a distance, Einstein would say. What is entanglement? It's the fact that if I have two particles, quantum particles, and they go far from each other, although they are far from each other, they can still, if you entangle them correctly, okay? Not all particles have this property. But if you do well your job, the two particles will remain entangled, which means strong correlation between measurement that you do here and measurement that you do there. I will elaborate a little bit of that. This is the experiment I did. Let us think of a photon. I can do a measurement of polarization on a photon. What is a measurement of polarization? If I send a beam of light on a polarizer, the light can go out either in a polarizer, you have two output channels. If light is polarized, that is to say vibrates, the electric field of light vibrates along the direction of the analysis of the polarizer, it will go out in the +1 channel. And if it is polarized perpendicular, it will go out in the -1 channel. And if it is polarized at an angle, a fraction of the beam will go up and a fraction of the beam will go down. But if you have a single photon, you are not going to get a fraction of the photon up and a fraction of photon down. A photon is a particle, cannot be split. And so if you send a photon, you will find the photon either up or down. When you find it up, you say, oh, my result was +1. When you find it down, you say, my result was -1. What can you do with that? Nothing. You must repeat the experiment many times, preparing the photon the same way. And if you repeat many times, you will look at the probability to get them up and to get them down. In the case of entangled photon like the one I was using, it looked totally random. Same probability to go up and to go down, and if you look at it, it looked totally random. Same thing on the other photon. Okay? On the other photon, I put a polarizer, and I make a measurement, and whatever the orientation of the polarizer, it sometimes goes up, sometimes goes down. Looks totally random. Now I pronounce the word correlation. Where do I have correlation? If I have two entangled particles of the kind that I could produce in my laboratory, and if I take the same direction for the two polarizers, then something interesting will happen. People who are here will still see randomly up and down. This one will also see randomly up and down. But the people who are far here and observe both sides will observe a strange fact. When it is +1 here, it is +1 here, and when it is down here, it is down there. When it is -1 here, it is -1 there. This is a strong correlation. I have a random variable, I have a random variable, but these random variables are strongly correlated. Okay, how do I know? Well, first, because I have done the experiment. But before doing the experiment, it is what was predicted by the mathematics of quantum mechanics. But Einstein said, look, if you have such a correlation, there is only one way, one reasonable way to understand this correlation, is to assume that from the beginning, the two particles has the property that will determine that it will be, for instance, +1, +1. Next pair, there is a property saying that it will be -1, -1. So far, so good. Sounds very reasonable, very scientific. The kind of conclusion that you draw when you observe that twin brothers or twin sisters have same color of eyes and same property. You say, of course, they have the same chromosomes from the beginning, when they were created in the belly of their mother. It's the same set of chromosomes for the two, and so no surprise that they have same color of eyes. But Bohr did not like that at all. It was a big debate between Einstein and Bohr. Because by doing that, Einstein thought he could prove that you need to complete the mathematics of quantum mechanics. Because the mathematics of quantum mechanics describes all my pair with the same mathematical tool, the same quantum state, the same wave function. All the pairs are described the same. But Einstein said, no. Some pairs from the beginning, you know they are going to be up. Some pairs, you know they are going to be down. And Einstein, who liked to think that you must complete quantum mechanics, said, you see, you must introduce supplementary properties. You need to complete quantum mechanics. And Bohr said, no way. Quantum mechanics as it is the end of the story. You cannot complete it. it was a long-lasting debate which was only about interpretation. There was no practical consequence. Einstein did not disagree on the result of the calculation. Bohr, of course, agreed on the result of the calculation. Until, in 1964, a man raised his finger, it was John Bell. He said, excuse me, if I take the point of view of Einstein, I show that there are certain restrictions on the correlation you can obtain by assuming joint property, etc., so-called hidden variable. There are certain restrictions, and in some cases, the prediction of quantum mechanics go beyond this restriction. This restriction is known as Bell's inequality, and some prediction of quantum mechanics violate Bell's inequality, cannot be understood as explained by this supplementary parameter. And now you have a fantastic situation. It used to be a philosophical debate about interpretation of the world, but now it's more than a philosophical debate. You can settle the debate. Time's up. So I go away, or I finish. If you don't want me to finish, say it. No, okay. Well, you know. So it was possible to settle the debate by doing an experiment. The first person to do an experiment was John Clauser. He was one of the laureates of the 2022 Nobel Prize. Okay. What I did more than Clauser did the experiment with the two detectors and found correlation. What I did more is establishing non-locality. Non-locality is the fact that while the photons are propagating, I change the orientation of the polarizer. And I change on the other side. And the result that I found was depending on the orientation at the very last moment. And this establishes the fact that until the last moment, the result can be as well +1 as -1. Same on the other side. Until the last moment, it can be either +1 or -1. But when the measurement is done, you get +1, and then instantaneously you get +1 on the other side. That's quantum non-locality. Quantum non-locality is at the root of quantum communication technologies. These fantastic properties of entangled particles, the fact that you have more information in the entangled particle than in the sum of the information that you have here and the sum of the information that you have there, this capacity to store more information is at the root of quantum computers. So this discovery of entanglement is a conceptual revolution. Observing experimentally that entanglement is as extraordinary as predicted by the equation is a scientific revolution. Establishing quantum non-locality is a scientific revolution. And now we are in the process of the technological revolution with the development of quantum computers and the development of quantum communications. And entanglement was imagined in 1935 by Einstein and his colleague. Then John Bell added his stone to the story 30 years later, 29 years later, 24. We did experiments, Clauser in 72. My experiment was in 82. And now we are more than 40 years later, and we begin to have quantum technologies. So once again, it's a long way from basic concepts to application. Thank you for your attention.
Merci beaucoup, Professor Alexander. Thank you. 接下来这段时间呢，那我借用大家呢来看一下我们荧幕的两侧，我们荧幕两侧有个 QR code。那因为在这个论坛当中呢，其实有非常多 新的创新跟科技研发，也欢迎您给予我们相当的回馈，以利于我们未来举办活动的时候可以有更好的呈现。Ladies and gentlemen, you are very welcome to scan the QR code for our questionnaire. If you've done the questionnaire, you can show your screen for a little gift at the Futex launch. 在我们的这个服务台当中呢，都可以呢利用这个 QR code 填写完问卷之后来交换我们今天特别准备的小礼物哦。For the next session, we're going to move on to the panel discussion today. The panel discussion featuring companies and startups from Taiwan, France, and Finland. In this discussion, we'll explore groundbreaking advancement in quantum computing, quantum communication, and quantum encryption. Technologies not only have profound impact on fundamental research, but also create unprecedented opportunities and challenges for the industry. 在这个论坛当中呢，我们的讲座会由来自台湾、法国、芬兰的企业跟新创公司来共同的参加。那从量子计算、量子通信到量子加密技术的突破，不仅讲到了基础的学科研究，更为产业带来前所未有的机会。So now we're going to proceed to the panel discussion. The panel discussion will be moderated by Dr. 张文豪 CEO of the Quantum System Promotion Group. 好，接下来呢，我们也会请到刚刚呢，其实提到这个论坛的讲者，包含了我们的蔡兆轩博士，以及呢，包含我们今天在来自台湾呢，有人保电脑、鸿海研究院，以及法国的新创公司 Condela and Pascal， 相当的精彩可期。所以接下来的时间，我们先邀请我们的语坛嘉宾来上台。我们首先呢，来邀請我們的語壇嘉賓 Professor Alain Aspect of Université Paris-Saclay. Bienvenue. Please be on stage for the panel discussion. 好，还有我们的 Professor 蔡兆生 of Tokyo University of Science. Senior Vice President of Compo Electronics, Mr. 陳希冠資深副總。Director of Quantum Computing Research Institute of Honghai Research Institute, Dr. 謝明修。Global Affairs Officer and Co-founder of IQM, Mr. Johan Bakhtiarian. CEO and Co-founder of Condela, Dr. Nicolo Somasky. CEO APEC of Pascal, Mr. Roberto Mauro. 以及我们今天的主持人 CEO of Dr. 张文豪执行长 CEO of the Quantum System Promotion Group. Welcome. 时间交给我们的执行长。
非常荣幸今天 Oh, sorry. I have to speak English. It's my great honor to moderate the panel discussion about the coming quantum eras. So we would like to discuss the opportunity for the Taiwan industry in the deployment of the quantum technology. So today we learn very much about the quantum entanglement. So now, before discussing the deployment of the Taiwan technology industry in quantum technology, I would like to go back to the very beginning of the quantum technology. Let's start by learning the quantum technology in the very beginning. So I would like to ask the question first to Alain Aspect. You are a pioneer in the atomic physics, quantum optics, and also demonstrate a very important experiment on the entanglement of photons, and also set the very important foundation of the quantum mechanics. So at that time, do you really anticipate that your experimental finding would be so significant in the quantum technology nowadays? And also, we know you moved to the laser cooling technology for atom, At that time, do you foresee the trapped atom can be a really workable quantum computer at that time?
The answer is no to both questions. When I was doing the experiment with a photon, an entangled photon, I thought that it was a wonderful problem and a wonderful goal, settling a debate between two extraordinary physicists, my heroes of the 20th century, Albert Einstein and Niels Bohr. Both impressed me very much. How could it be that they have diverging opinion? And I had a chance to settle the debate between these heroes. This was my only motivation. And the proof that it was my only motivation is that after settling the debate, I decided to change field. And as you say, I decided to go on something totally different, which is laser manipulation of atoms. And I joined the group that Claude Cohen-Tanouji, famous physicist, was establishing in his lab. He wanted to start a research operation on laser cooling of atoms because he had heard of the first experiments by Bill Phillips in the United States, and he thought that it was a moment to start, and invited me to join him. And I certainly agree because I thought that about entangled photon, I had done all I could do and it was time to switch to something else. And again, when working on laser cooling of atoms, our goals was to control the motion of atoms so well, to have the atom moving so slowly that the temperature would be extremely low, closer to the absolute zero than anybody had done before. And we did it. We did an experiment in which the atom was displacing itself so slowly that the velocity was less than the velocity that an atom takes if it was initially at rest, and then it emits a single photon. And then there is a small recoil, not much. This is called the one-photon recoil. I did an experiment with Claude Cohen-Tanouji using some smart quantum effect. I will not try to explain now. But I did an experiment in which the velocities of the atom was definitely less than the one-photon recoil. And the goal was just to play, to reach a state of matter when the temperature is so low that some new property could happen. And eventually it happened. We were not successful in doing that. It was a demonstration of Bose-Einstein, Einstein again, demonstration of Bose-Einstein condensation. And then trapping atoms, we could do it, but we were trapping an ensemble of atoms. And discovering the trapping of a single atom was discovered by serendipity by my first PhD student, Philippe Grangier. He had participated in the experiments on test of Bell's inequality. Then he has been a postdoc in the Bell Labs in the United States. And he came back to France and wanted to use cold atoms to do quantum optics. And one day, so he was trying to trap a few atoms in a well-focused laser beam. And one day, he observed a strange property. Sometimes there was one atom trapped. Sometimes there was 0 atom trapped. But never 2, never 3, never 4. He was surprised. He eventually understood it. And this is a basic tool for the computing with neutral atom that you have in Pascal. And it was a discovery by serendipity. But serendipity means that when you observe something surprising, you begin to think hard and eventually you understand it. And it is well understood now. And to finish, because I am too long, I know that I am too long, they will show me a sign and say, shut up. But the only comment that I want to do is that when doing all these things, I never thought about application. But I always say to my students, I'm not gifted to find application of our research. If you have good ideas, really develop these ideas. Think about it. And this is the reason why when they got good ideas, they came back to me and say, we have this idea for applying the research that we have been doing. What do you think? And after observing, I say, yes, good idea. And then they ask me to come with them, and this is how I am involved in these societies. Like Pascal, I am a co-founder of Pascal. Like Candela, I am member of the advisory board of Candela. And always because the people who have founded this society have listened to me when I say, I cannot myself imagine application, but if you have idea of application, go, do it.
Okay, thank you. So today we also have a very important pioneer in quantum computing based on superconductor. So Professor Tsai, he is a very important person. He demonstrated the first superconducting quantum qubit in 1999. And then a few years later, he demonstrated the control NOT gate and also universal quantum gate in 2007. So I would like to ask Professor Tsai about a similar question. So at that time, do you also foresee that your experimental finding would lead to a workable quantum computer? And at that time, you were working in NEC. And did NEC have the ambition to build a quantum computer at that time? Yeah.
Speak and it will work by itself.
Yeah.
Oh, okay. All right. Can you,
Controlled by AI.
It's magic.
okay. So, good question. Right. Okay. At that time, that was end of the last century. We are searching for macroscopic quantum coherence, which is, something holy grail in superconductivity. People are searching for that for a long, long time. Can macroscopic object behave quantum mechanically? And finally, we observed, we have this quantum superposition, Rabi oscillation, everything like that. That's great. We did it great. And then when we are writing papers, we thought about it. And then we hear something about qubit or quantum computer, which is not our field. But then, I scratched my head. Oh, this is qubit, actually. And so I said, in the paper, we should say this. Qubit, that can be applied to quantum computer, which I don't know anything about it. Because, but then our colleague, two co-authors, Yasunobu Nakamura and Yuri Pashkin, younger guy, they don't like it. But I said, NEC's computer company, and we should, sell this. So finally, I pushed that in. And since this is solid-state system, can be, scaled up. So we tried to sell that. So, of course, I didn't have any idea how to build quantum computer, but it was included in my paper. And as you ask, okay, one thing is that after 25 years, I never anticipate this field will develop so fast. In the beginning, NEC actually, in the lab, we are in the fundamental research lab, they support us. And occasionally we have papers and we have press conference. We have many press people. And then we say, well, we have qubit, 1 qubit, 2 qubit, gate, and they are really puzzled, and they don't believe anything. And they ask, finally, many news reporters say, oh, NEC is a serious company. Why you are doing something like this? But, you know, my manager kind of support, no, this is important. And finally, so this goes on for many, many years. And the press are so, they don't believe anything about scientists, says. And so finally, I quit I was, you know, because of my age, I left NEC at 2015, and they stopped the project. And then now people are, the news conference, the press will always ask, why you stop doing this? You can't win. Well, that's my answer.
Thank you. So from the very important pioneer, we know that all the quantum technology actually were initiated in the research lab. But now they are also actively going into commercializations, especially in Europe. So quantum ecosystems are well developed in Europe, and that fosters collaboration between the government, academia, and also industry. And so they got the significant global investment to accelerate commercialization. So now let's take a look at some example in Europe about quantum startup company. The first one I would like to ask Juha. So IQM in Finland, I think it's a leading company in building superconducting quantum computers. Could you share the experience of IQM on how to transition from a research lab to a startup company? And what have been the lessons learned?
Thank you for the question, and very happy to be here and in this panel together with the pioneers. So it doesn't happen that often for me. So first of all, there are like a lot of differences. So the requirements in industry are very different from that in academia. The goals are different. So we are serving the customer. We are building the product instead of a research paper. So we start there where the academic research stops. Maybe the one major difference, what is very specific for quantum computing, is that geopolitics. I want to mention that one. So I'm citing here Ken McCallum, the general director of MI5. So he's not the boss of James Bond, if you know James Bond. That's MI6, and this is MI5, so it's for different purpose. If you are operating at the cutting edge of tech in this decade, you may not be interested in geopolitics, but geopolitics is interested of you. And this is exactly what we are now experiencing in quantum computing. So there is a lot of geopolitics in place. There are a lot of export control. There are a lot of governmental fundings to the critical technologies. So the quantum computing is very special technology. It's not just another technology. And particularly, it's a disruptive technology in future. When the quantum computers are more capable, they can change the world. So the countries are interested of quantum computing particularly for the reasons of breaking encryption codes, sometimes after a long time, not in near future. But anyway, this is the core of national security, and that's why there is so much interest. And then there are other reasons. But about the mindset, so we have been hiring more than 100 quantum PhDs. They come from academia, and there are a lot of things that they have to learn. So that the change in the mindset is the big one. I already mentioned the the customer focus, which is new for many. And the another one is the teamwork. In academia, each researcher is basically working on his or her own thesis project, but in a company, it's a joint effort. And another one is about the quality. So it's not enough for us to build one hero device, but we have to build a product which is reliable, it's repeatable, it's everyday in top-notch condition. Then we are concentrating on uptime and the user experience, so it's easy to use, not only that it can be done, things can be done. So let's say that reaching like high fidelity, 3/9 of fidelity, it should be every day for every customer job. And then the final one is the scale. So we are taking quantum computing seriously. So it's going to be a big thing in future. And that means that we have to fundamentally change the way how we are building quantum computers, not only making one of them, but many of them and maintaining them and making them industrial products. So we have been delivering more than 6 systems which are used by the customers in HPC centers around the world. And it's not enough to have a PhDs researchers there, but we need many other professions in different fields. And one particular challenge for us is the cabling. So in a cryostat of 150 fully tunable transformers with tunable couplers, we have more than 2 kilometers of RF cable and tens of thousands of connectors. So that's a lot of work to fasten them all and have in a top-notch condition all the time. So we have to develop new solutions. And for that, we need to have a good network of partners, technology partnerships needed with like-minded countries, with the best companies around the world, and good subcontractors, vendors, and value chain has to be built so that we can make it. So no one will make it alone in future, but we have a collaboration. We need standardization, and of course we need to involve the end users and build end user forums where the customer experience is communicated. So those are my observations.
Okay, thank you. So now let's fly from Finland to France. So Nicolas, so Quandela in France is a European startup that provide photonic quantum computers. So can you give us an overview of how the company involved from academia lab? What's still the challenge in Quandela?
It's definitely not an easy path. And first of all, I want to start from the beginning, how the technology and the idea started. And it happens that the research laboratory where the co-founder were working is just a few hundred meters from the laboratory of Professor Aspe. And we are huge fan of Professor Aspe and the photonics. So we started to ask ourselves, if the complexity of 2 entangled photons is so high, what can we do with 10 entangled photons, or 100, or even in millions? And that's we started to think, indeed, about the applications. And it turns out that manipulating this massive amount of information hidden in millions of entangled photons, we can build up algorithms for quantum computing. And that was the driving force as a researcher. But then we also realized that, as is in the title, the final user are industries. So we cannot just think with the research and scientific mindset, but we have to work very hard on the engineering. So we started right away to drive our roadmap and forcing ourselves to make objects, modules, quantum computer, and algorithms that are user-friendly, that are products that can work repeatedly every time in any kind of environment. So first challenge, indeed, create products and think about the development you do is for a final user. And now the challenge goes forward because as well now in the title, the industries are not only the user, but they are the partners. They are the enablers for us to scale up this technology. And I like the fact that we now speak about technology, but if we want to make this very valuable, we have to speak about quantum industry. So the mindset has to be there, and the work with the industry is the next challenge to make this technology more useful and also massively produced at scale.
Thank you. So now we move to another company. So Roberto, Pascal in France is a European startup that provides a quantum computer based on trapped atom. As a CEO in the Asia Pacific region, so do you notice any difference between the quantum ecosystem in Europe and also in Asia area?
Thank you for the question. I'm very happy to be here. Of course, I will be very careful about anything I say, since Pascal is co-founded by Professor Aspect. But so to your question, I think, of course, there are many differences, but also many similarities. So let me start maybe by talking about the science development. The science community is a very international community. So you have scientists from all over the world working together into advancing the science. So scientists from Taiwan, from France, from Italy, from North America, US, they move from one lab to the other. And this is creating a lot of very interesting exchanges at the scientific community. And we definitely believe that this benefits the science community globally, and it's very beneficial for all regions. Now, if we look a little bit closer now at downstream, basically on the development of the technology and of the applications, then we start seeing some differences. Today, effectively, Europe and North America are probably more advanced in terms of their science labs research with scientists from all over the world, whereas Asia is a little bit behind, but is already looking at very carefully the technology and the applications. And so there is a lot of benefits, of course, in these, various approaches and working together. As Mr. Vatainen said, of course, there is the issues of geopolitics. And so Pascal is a company that is based in France, but it's a global leader. And so we already have, of course, a hub in France, being our headquarters, but we already established a hub in North America, in Canada, to have, a foot in that part of the world. And we are now establishing a third hub in Asia, to make sure that we can benefit from the best of both worlds, the best science and the best technology. And by the way, we like to say at Pascal that Pascal is a mix of science and engineering. Of course, we believe we have some of the best scientists in the world, but we also have some of the best engineers. Our CEO actually worked 15 years in the industry before founding Pascal. And so from the very beginning, he had this vision of bringing to market useful quantum computers. And so from the day one, we developed full stack approach. And this is why today we strongly believe we are the global leader in neutral atoms quantum computers. We've been providing computers in Europe, in the Middle East, and especially to the first enterprise customer who bought a 200 qubits quantum computer, selected Pascal for that reason. And then we'll stop here.
Okay, thank you. So now we fly back from Europe to Taiwan. So today we have two panelists from the two biggest companies in Taiwan. So the first question I would like to ask to the director, Director Xu. Honghai, also known as Foxconn, was the first Taiwanese company aiming at developing quantum technology. As a director of quantum information science in Honghai Research Institute, so could you share some original thought of the company? And do you see the opportunity of Taiwan industry in the coming quantum era? Thank you.
Okay. Hello. First of all, I would like to thank the organizer for inviting me to this wonderful event. I have been learning a lot from Alan Esbeck and Professor Tsai and these gentlemen. Regarding the questions, yes. So I'm actually quite surprised when I first received a call from our chairman that he wants to set up a research institute on quantum computation. A very easy answer to this question is that our chairman has a vision for the long-term technology path. So even though Foxconn right now is focusing on EV, on robotics, and on digital health in this coming 5 years, but for a major international corporations, you need to have a even longer term of visions. And quantum computation is currently the industry that our chairman believes that in 6 to 10 years, it will become very, very important. So that's why we set up this research institute. We foster technology within our research institute. Not only we have a theoretical teams to develop quantum applications, quantum error corrections, more fundamental quantum research. We also have laboratories that focus on trap ion technologies. In-house, we have our own lab to manufacturing quantum qubit. We believe that this sector will become very important in the future. Regarding the second questions, yes, it's never too late. I think there is still a long way for the quantum technology to become mature. At this point, there is no clear winner of each platform. I'm sorry to you guys. But from the theoretical point of view, every platform has their pros and cons. Trap ion has very clear advantage on long coherence time, identical qubit, but there is unclear path to scale up. For superconducting, then it's relatively easy to scale up, have more qubit, but then each qubit is slightly different. You need to spend a lot of time on calibration. So I mean, what I want to say is that there are a lot of challenges and also a lot of opportunities. So this is a good chance for the Taiwanese company to move into these sectors. Yeah.
Okay, thank you. So the next question moved to Compo Electronics. So Compo Electronics is one of the world's leading manufacturers of laptops, PC, and also servers. So Sikuan is a senior VP of the company. So do you view the development of the quantum computer from the perspective of a conventional computer manufacturer?
Thank you for the question. Professor Asper, I have an easier explanation of quantum entanglement for the average person to share with you. I was telling my wife that I'm going to have a forum with Professor Asper today. And she said, the Alan Asper? I said, yeah, the one and only. And she said, what do you know about quantum entanglement? I mean, are you not nervous? I said, well, you only get nervous if you know something about it. And if you don't know anything about it, I'm not nervous. So I said, honey, so think of two of us as particles, right? And we have been married for 30 years. So think that we are separate, very far apart from each other. We would still think alike. We would still hate each other. But we still think exactly the same direction. That is entanglement. And she get it right away. So I was saying that at least she didn't ask me what EPR paradox is. So there was a good explanation for her. But anyway, having said that, it's a joke, but it's also not a joke because I come from a industry background, but also as a designer, trained as a designer and also as a marketeer. And one of the things that conduct a recent research, I think it's online and cross globally, and find it very interesting, I want to share with all the audience and all the respected guests here, is that because of the hype of AI and all these quantum computers, supercomputers, there's an online survey that was asking like 2,500 samples across the world, like what is your expectation of AI and related enabling technologies in the future, and what is your fear? And the answer is quite surprising to me. They speak very less of expectation because they have no idea what that means. They don't have no idea what artificial intelligence means. But they are very fear that it is going to take away immediately their job. And this is regarded both white collars and blue collars workers. So the fear now in the market is that the consumers are very aware that this technology might take away their survival skills and not necessarily adding plus to them. And that is the reason that for this year, the entire global AI PC, the so-called AI laptops and desktops alike, are not selling as aggressive and as what we expected globally in the numbers. We thought that people would like, oh, of course, I want a newest generation, the AI PC, but it's not. So it really explains the anxious and the nervous from the end consumers that they do not know what this is. And we cannot communicate the characteristics of quantum computers, interference, superpositions, and entanglement to the end consumer. They have no idea what these are, and this is no marketing talks. So one of the ideas is that please, if you are all here and doing all these quantum mechanics or quantum computers, work with designers, because I think all this user experience and user IDs, industrial designers, they have limitless aspirations and inspirations to work with you guys, software, hardware, and quantum computers technologies. I think the sky is the limit. I think there's a lot of potentials, but first we need to sort out what the market need is and how to attract the market. Thank you.
Okay, thank you. So now I have a question to both the two pioneer here. So quantum technology are still developing. And so Professor Aspect and also Professor Tsai, do you foresee any of this technology can lead to transformative breakthrough? How should academia, industry prepare for and or respond to this future development? What would you like to suggest to Taiwan, include government, academia, or industry? So, Adam first.
I don't foresee anything. All my career, I did not anticipate what I would do in my lab after 2 years. It turns out that in my position, I had to write every 4 years a report about what I've done and what I intend to do. And so 4 years later, looking at the report, I could see that the first year I had done what I was planning, and after the second year, I had done something different. So don't ask me to foresee anything. I'm not good at all for foreseeing. But I think I am not bad to react very rapidly on a new idea, either from me or from colleagues. It's very important. Now, what is the advice? The advice is continue to support basic research and to support exchange between basic researchers. Quantum computing is so difficult that we will be able to have a good quantum computer only by adding up all the discovery or the progress made by the various academic laboratories in the world. Now, when this happens, and we have already some industries, we need many quantum engineers. And we will have only these quantum engineers only if you support education. So give grants for PhD students in quantum. Give grants to have Taiwanese PhD students coming to make a PhD in France, and vice versa. I think that the only good advice I can give is give money to support exchanges between researchers and also exchanging between students. I think that long-term student and a PhD is long, it's at least 3 years. long-term students are people who are going to be the best ambassadors between the various countries, ambassador of science between the countries. And my advice is put money in education and in exchanges.
Thank you. So, Professor Tsai?
Okay, I guess the same questions. How do you foresee? Foreseeing science, it's very hard. It's almost impossible. And foreseeing technologies, maybe you can do it to a certain extent, I believe. And now we have many technologies, and we can foresee in 10 years it can be reached certain place. But if you ask, what can quantum computer do? You know, if you ask me, I cannot really answer. You know, of course, because researcher cannot really foresee the application. You know, when transistor was invented, Bell Lab said, people asked them, what can this do? Oh, maybe this is good for hearing aid, right? You know, IBM, they said when they have these computers, they said, okay, maybe you need just 2 computers to do this trajectory calculation or reading secret code or something. But no one foresee that now each person has like two PC or 2 computers in your pocket and doing all sorts of things. A quantum computer, I believe you can do many things, but I cannot really foresee. About what
Suggest.
suggest. Yeah, okay, so industry and academy is very different. So one should have something complementary to do. You shouldn't do the same thing. Academy, maybe you should invent some new things, new ideas, training students. And industry, they have more, you know, research power and pursuing certain target. Something like that. What else? I forgot. That's all the questions?
Yeah, that's fine.
All right, okay, good. Okay.
So I would like to ask another question to the rest of the panelists from industry. So the market for quantum technology is still in the very early stage. The world is actively seeking the killer applications to boost it. So what do you think what is the most likely killer applications? And what would you like to suggest to Taiwan? The same questions? Government, academia, or industry? So Yoha, you first.
Yeah, thanks. First, I would like to a little bit disagree with the question. So our thinking is quantum is closer than it appears. So actually, already now there are a lot of applications for educators, for researchers, for innovators, what you can do with quantum computer as they are now. One of our competitor published yesterday their figures. So on average, actually their users are using 11 qubits on the system. So that's not so much. And those kind of quantum computers are now widely available. And then there are, of course, the communication and the sensing applications of quantum technology, which are more mature and already like semi-commercial use. And where, let's say, we can maybe see the already now like semi-commercial applications of quantum computer are using them as quantum random number generators. So for certain security applications, they are already very valid. And then what comes to like a second stage, I see a lot of progress in hybrid classical quantum algorithms. So it is quantum computers are getting integrated to the HPC centers. We have been involved in many of the projects like that. And their quantum computer will make only part of the job. And looking in that sphere, where are the applications? So we should look at let's say, the biggest workloads of HPC. So those are computational fluid dynamics and nowadays AI. And actually there are quantum applications in both of those, how to accelerate them. It might be, especially in the case of the AI, that the quantum computer is a little bit as a side role, but anyway, if it can accelerate even 1% of the training the big AI models, it's already done its job, so it's worth of investment. So that is actually where we are now foreseeing like a lowest hanging fruit. But then, of course, if you look at the domain as a whole, there are, I think the most of the application in quantum chemistry, materials research, and different kind of optimization problems. So those are maybe the most active areas at the moment.
Okay, thank you. Nicholas?
Yeah, I would like to try to answer to this question with a very simple example, taking as an example a company that you all know very well, which is NVIDIA. So NVIDIA is a world leader in building computers that power AI and machine learning, and we can see it all over the place. But the processor that they started to develop in the 90s, they are called graphic processing unit. Yeah. So they were developing a tool to enable new generation of graphic for video games and for developers. And they didn't even think that machine learning could be their killer app. So we probably, in quantum computing, don't know yet which will be the killer app. So what to do with this? What do we take home? Well, some people say just focus on making the best quantum computer and put it out there. Yeah. Make it available. So we started in late 2022 with we are the first European provider with the open cloud access. So the first quantum processor, as it was, we put it out there for the user to play with it and get feedback. And we improve each year. So we are now releasing the third processor. So a suggestion for the institution, the industries, the researcher, is just go directly on the cloud, play, and start to learn as a student to develop application and help us to find a way to make them the most impactful possible.
Okay, thank you. Murato?
So
Roberto?
Yes, I will echo some of the things that have been said already, of course. So first of all, quantum computers are already a reality. Of course, there is lots of improvements still needed before we get to a general purpose quantum computer, but we can already use today quantum computers to solve certain problems with good results. Then I agree with Nicolas that who knows which killer applications will come up. We can, however, think about the origin of quantum computing as it was explained initially by Richard Feynman, saying that in order to simulate material, material is fundamentally quantum by nature, and so you cannot do that with a deterministic computer. So you would need a computer that is based on quantum particles to simulate material. So probably, new material science is an area where early we can see some good developments. And then I would also like to say that I agree with Dr. Xie that, in the long term, it's difficult to know which technologies will win. But maybe looking at what's happening short term can be an indicator of what may happen in the long term. May not. But so what we see in the market today is that some companies are starting to make interesting partnerships. Like Pascal and IBM announced a partnership in June this year to work on a common approach for quantum-centric high-performance computing centers. And of course, IBM is developing superconducting technology, and Pascal is developing neutron atom technology. Then after a few weeks, we saw Microsoft do a partnership with atom computing. Same thing, superconducting and neutron atoms. And then just Tuesday of this week, Google announced a partnership with QEra, again, superconducting and neutral atoms. So there seems to be a pattern where for short-term applications, large companies are looking at neutral atoms as the technology that can bring value right now. And we like to believe, and that has been demonstrated scientifically, by the way, that neutral atoms is also very well positioned as a technology to develop fault-tolerant quantum computers. And so, we like to believe that neutral atoms is well positioned to develop general-purpose quantum computers. Not in 20 years, not in 10 years, but probably much sooner than that.
Yeah. Thank you. Ming-Xiu?
Okay, based on the property of quantum mechanics, namely entanglement and superposition, the domain expert actually believed that the following 4 sectors would most likely have a significant impact by the quantum technologies. That is computation, communication, simulation, and metrologies. So this has been identified in many countries' national quantum programs. Because of the time, I don't want to go deep into why quantum properties would significantly impact these 4 sectors. You can just search Google it and look for the answers by yourself. I have another way of categorize these quantum sectors: hardware, software, and applications. Hardware is easy. So depending on different technologies, you would have different core technology to be developed on. So for example, superconducting, you would need a core QPU that relies on Josephson junctions. And besides that, you also need to have like enabling technologies like refrigerators, cryogenics ICs, and et cetera, and RF control. For the atom system or ion system, then you would, except for the atoms or qubit itself, you also need to have like lasers, silicon photonics, etc. So this is the hardware opportunities that if companies want to enter, you can look for the specific technologies. Software is also easy to understand. Each hardware needs to have a corresponding software to be run on it, be it very low-level assembly languages, automatic control systems, to be very high-level applications, even operating systems. If you talk to some of the Microsoft researchers, they already have ideas like we need to create operating systems for our quantum computer in 20 years' time. And then applications that you can think of all kinds of applications, like if you some major bank, for example, JP Morgan in US, they have teams that trying to using quantum algorithm to optimize their portfolio, portfolio optimization, minimize their risk on certain behaviors, things like that. So there are a lot of possibilities that you could use quantum algorithm to speed up your problems. But of course, there are a lot of things that still need a lot of research. We only know some heuristic argument. There's no research no result or no theorem to tell you that yes, quantum computation indeed provide advantage. So that's why if I want to suggest, I think governments or universities, even corporations need to put in more research to let us understand what quantum computation is useful for. Yes.
Okay, thank you. Su-Kwang?
Thank you. I'm not sure these are the areas we could be right, we could be wrong, but these are the areas that my company is interested in, and I think also some other companies in Taiwan and around the world. Cryptography and cybersecurity, I think, is one major areas that quantum computing is looking at. And I think also climate modeling and weather forecasts, drug discovery and development, finance modeling and risk assessment, optimization of supply chain and logistics, material science, and last but not least, I think AGI and ASI, so general intelligence and super intelligence, of course. These are the areas that in general, I think the entire quantum computing community are working on. Either we're right, either we're wrong, time will tell. You talk about, is there any like low-hanging fruit? To share with you, from the survey I just mentioned, 2 ideas from the around the world people are hoping really for that comes up like top 2. First of all, a quantum drug interaction checker. So like if there is a hardware or software that can help people on a quantum level, you can check the molecular interactions between the drug and the body so that you can get very precise and accuracy doses, and also you can prevent, let's say, side effects. The other thing I think is all major mayors in the big cities would prefer this. I think this is a thing called quantum traffic flow optimizer. I think going to work from 8 to 9 o'clock and then going off work from 5 to 6 o'clock is probably on this planet the most carbon footprint consumption activity. And before we can change that behavior, maybe quantum computer can help us to how to prevent traffic jam by manipulating and giving guidance to thousands of vehicles simultaneously. So these are 2 herring foods. You mentioned last question, give Taiwanese government some advice. My humble opinion, or maybe this industry humble opinion, we don't think quantum computer is here or in the future is here to replace the so-called classical computers or conventional computers. I think one of our guests also mentioned that. Taiwan is very special in and very expertise in, let's say, silicon-based technology. So, of course, quantum computer can solve problems very fast. You know, I just watched a YouTube yesterday that, you know, for a very hard problems that's solved by classic computers for 47 years, take only 2 seconds for quantum computers. But for daily issues, we don't kill a bird with a cannon. So there will be an agent in the future that tell us what kind of problems go to quantum computer and what kind goes to classical computers. So they should coexist for the sake of ESG and UN SDGs and environmental friendly. So Taiwan can focus on quantum/classical hybrid chips production and its supply chain. I think this is the best that we can offer, and also put us our advantage and also put us on the front end of this emerging technology. Thank you.
Okay, thank you. So now we still have a few minutes, and I was told not to end up this panel discussion later than 5:10. So we still have a few minutes. So I would like to call some question from the audience here. So do you have any question you'd like to raise to the panelists here? Anyone? Yeah, please. So who will give her the microphone? Who?
Thank you for all the panelists' great information and introduction. And I would like to raise my question because I fully agree Sequen's opinion that traditional computing and quantum computing would cooperate together. So in terms of this direction, would that be some industrial standard defined for the collaboration between these 2 different computing frameworks, and how Taiwan industry can follow up in this standardization trend?
Do you hear the questions? So you raised the question so Johan, you can.
Yeah, this is actually a very good question. So actually, the standardization in the quantum domain has only now started. There are no quantum standards yet internationally. So there is ISO, IEC, JTC 3 committee established, and they have started the work. And this domain, this HPC integration of quantum computer is also very new. And let's say that there are leading high-performance computing centers like LRC in Germany, RIC in Japan, Oak Ridge, US, and others. where this is actually a research level problem. So, but let's say that the solution of each of those centers is kind of converging towards let's say, a little bit similar direction. And since all of these centers, they usually they prefer to use open source software, and they are sharing their solution. So I believe that very soon we will see like alignment between the actors how this is done. But this is still like open research problem to a large extent.
Yeah, thank you. Do you want to share your?
Yes, it's indeed a big development today. At the core of, for example, Europe, consortia of supercomputing centers that are acquiring today quantum computers exactly for the purpose of working internally on the R&D necessary to bring the classical and quantum computing together. And this goes on the programming level, but it goes also on the middleware level. The two objects needs to be close to each other, but we cannot really put classical object very close to our qubits. So at which point we bring the bar down and we make this computation efficient, considering that these hybrid algorithms require a back and forth of operation from a quantum processor to a classical processor. So this is, as I said, algorithm level, protocol level, and hardware level. So suggestion is to start to work as soon as possible.
So people from industry seem to, yeah, please.
Yes, maybe if I can add just one more element. So of course there is the work that is being done at the standardization bodies level. There is work that is being done in the various regions of the world, especially in Europe. And then there is the work that is being done by companies, I would say independently from those first two. So the partnership between IBM and Pascal has exactly that purpose, to work on a quantum-centric, high-performance computing software architecture in order to be able to basically direct the workloads to classical computing or quantum computing, depending on what is most efficient or effective.
Yeah, thank you.
So indeed, this is a very important question because companies started to think about how to integrate it, quantum computers along with classical computers. But from a theoretical point of view, nothing is known. We do not know how to break down a very complicated questions. So we don't know how to really leveraging some the powers from both sides, right? In quantum computation, we know that it is very good for structural questions like a Fourier transform. But for the classical computation, it's very good for doing basic calculations, additions, subtractions, integrations, etc. So it's largely unknown. But I would like to use this opportunity to also promote one of our results that just announced a week ago. This is done between Hon Hai Research Institute and NVIDIA Research. We look into these transformers, like these GPTs, right? And we know that transformer has very complicated structures. It has layers over layers of neural network. Which part should you replace it by a quantum algorithms, right? So we did a very preliminary study, so you can look for our papers online, that we managed to replace one of the final layers, and then we could significantly reduce the parameters that is required in the training phase. So I think this is, at least to the best of my knowledge, one of the very interesting attempt to attack this kind of questions.
Okay, I think this time is limited. So if you have questions, anyway, you can find a chance to discuss with them. So I would like to close the panel discussion. So I would like to thank all the panelists to share their idea and also opinion and also experience on the quantum technology. So let's thank all of the panelists again. Thank you.
再次的掌声，也谢谢我们中华纸上 ，Thank you all. Would you like to take a photo together? Yeah. Okay. Okay. The cameraman. Yeah. Okay. All right. One more. Okay, a photo together. Please look at the cameraman. Is that okay? Yeah. 好，现场稍等一下下，我们执行长好像还有话，还有那个 Professor Alan Asbeck 还有一些话想跟大家说一下。
Yeah. I actually see the United Nations declared 2025 to be the International Year of Quantum. So I originally want to ask Alan Asbeck about who will be the quantum heroes and whose life and work you would like to most to see celebrated.
Yes, my hero is Einstein. Einstein and the quantum revolutions. This small book is quite cheap and you should read it, because when I started working on the EPR problem, many of my colleagues would tell me, look, Einstein was a genius about relativity, but he did not do many things interesting in quantum physics. This is 100% wrong. Einstein was a fantastic pioneer on quantum physics. This small book tells you the story, and I advertise the new book. I have given the manuscript to my editor in France, and we will immediately do a Chinese translation. And the title of that book in English is If Einstein Had Known. What would have this say if he had known about entanglement being observed in the lab? If he had known about quantum computing? What would have been the reaction of Einstein? That is the subject of the book who is now in print. So I want to advertise that, because I want to advertise Einstein as the hero of the year 2025.
Okay, thank you.
Thank you. Okay, they asked to take a photo by standing together. Yeah, standing together. Yeah, the last photo. Thank you very much. 我们再次给予台上的所有讲者一个热情的掌声，再次感谢他们，谢谢。好，我在这边呢也同时预告一下呢，未来科技馆呢在接下来几天还有很多精彩的活动，大家呢可以来到我们服务台前方的 schedule 来 check 呢，接下来还有很多精彩的内容，可以呢更好的来了解我们关于量子的内容。好，接下来还是一个赞的手势 for the thumbs up picture please. Okay, thumbs up. Okay, thank you. Very Chinese style. Thank you. 好，再次掌声。Thank you. Please take your seat. Thank you very much for joining us today. And that's it all for today. Thank you very much. Merci beaucoup, grazie. And we wish you a wonderful day. Bonne journée and bonne journée. Thank you.